Alright, so for this video we're going to be looking at these two cases that are described by this problem. One in which the temperature of the coolant goes from 300 Kelvin to 290, and then the second one where the temperature of the coolant goes from 300 Kelvin to 305 Kelvin. So I already showed you how we derive for the ordinary differential equations in our previous video, and I have a screenshot from that video over here so we can reference the equations that we derived when we're simulating it, but we're going to be simulating this using Python. So I've opened up a blank Python workbook, and first thing we're going to want to do is import the libraries that we want to use. So first we're going to want to use NumPy, because that's just basic math library, and then we're going to want to use the solve IVP function because we have an initial value problem, and that's what solve IVP solves. So from scipy.integrate, we're going to import solve IVP, and then we're also going to want to plot results. So from plotly.subplots, we're going to import make subplots. Alright, so next thing we're going to want to do is we're going to want to input all of the parameters and the values that have been given to us for this problem so that Python can find them. So we'll start with Q. So Q is going to equal 100 liters per minute. Then we'll have concentration of A going in. It's going to equal 1 mole per liter. Then we're going to have, so we're going to use T for the tau because it's temperature. So we're going to have the temperature that's going in is 350 Kelvin, and then we'll have the volume is equal to 100 liters, and then the density, we're going to use just a lowercase p for that, is 1,000 grams per liter, and then heat capacity is equal to 0.239 joules per gram Kelvin, and then we're going to have delta HR equal to 5e to the 4th joules per mole, and then we'll have E, so ER I'm going to use an underscore because you can't use slash as a variable name, so we're just use an underscore. So E over R is 750 Kelvin, and then K naught is equal to 7.2 E10, and that's 1 over minutes. And then we have UA, which is equal to 5e to the 4th joules per minute Kelvin. And then we have our initial condition, so temperature of the coolant is equal to 300 Kelvin. We'll have and then we'll have the concentration of A initial is equal to 0.5 moles per liter, and then the initial concentration inside the system is equal to 350 Kelvin. So we have all those. Enter those in. Oh, I forgot to comment that out. Alright, so next we're going to want to start defining the function that we want solve IVP to solve for. So So over here, we're look at these equations. We're going to want to put these two equations in the right-hand side. So we're going to define right-hand side, and solve IVP requires that you put the independent variable in first. So for that's the temperature, not the temperature, the time, and then it wants a vector of the independent variables that you have. So then we can unpack that vector into the concentration of A and the temperature. And basically you can put these in either order that you want. You just have to keep it consistent throughout the code. So we're always going to want to put our concentration of A before our temperatures. Alright, so let's return the right hand sides of these functions. So we'll return them as a vector. So the first one we're going to use concentration of A. As I said, we'll always do that one first. So we'll have Q divided by volume times concentration of AN minus concentration of A minus K times concentration of A. Alright, and you can see we got a little error marker there that we haven't defined K yet, so we can do that. So K is equal to the Arrhenius equation up here, so that K is equal to K naught times NP dot exp. So that's how you type the E, and then negative ER divided by the temperature. Alright, so then we have K. So next we move on to this temperature equation. So we've got the temperature initial minus the temperature times Q divided by V plus delta HR times concentration of A times K divided by the heat capacity times the density. Move that over so you can see it. And then, I just realized that should be a minus sign right there, not a plus sign, because if you think about it, so this is, the UA is the heat transfer from the inside of the tank to the coolant, and heat is going to be lost because this is an exothermic reaction and the coolant is cooling it down. So the temperature should decrease based on the heat transfer between the tank and the coolant, and right now we have it increasing based on that amount, so we'll just fix it right here. That should be a negative, or a minus sign. So, sorry about that. So we'll have, so everything else is the same, and then we have temperature minus the temperature of the coolant, and then divided by heat capacity times rho, so the density times the volume. And then you can see we're getting another error here that we haven't defined the temperature of the coolant. We can go ahead and define that up here. So the temperature of the coolant is going to be different for each of our simulations. So in the first one, we want the temperature of the coolant to end up at 290 Kelvin, so we'll start with that one. And then we can change this later when we look at the second situation. So enter that in, and our error should go away. So we can enter this in, and everything looks to be good. So let's move on to solve IVP. So yeah, so solve IVP. So first thing we put the function in, so that's right hand side. Next, it wants the range for our independent variables, so we can go from time 0 to maybe 10 minutes. But actually, probably what we want to do is create a variable with the end time so that we can use it later for our plotting, and it'll be the same, and we don't have to type it a bunch. We can change it if necessary, so it's better to have a variable, everything in one place, than to, type in a number a bunch of times. But we're pretty safe to start with times 0, because that's, right when the simulation starts, so that makes sense. We can just type the 0 in there. And then, next thing it wants is, our initial conditions. So, again, we're always going to start with concentration, because that's what we decided to do. So, concentrations of A naught, and then temperature naught. And then we're going to want to put our method. So our method is going to be do. You can use any method you want. This is just the one we're going to be using. And then you can use the dense. And then we're going to set dense outputs to be true. True. Alright. Shift enter on there. Oh, I forgot to shift enter up here. Alright. So now you can see this is what we're looking for right here. So we want to get that out and we'll put it in the variable sol. Alright, and then enter that in. So you can see if we just put sol in, we just get that attribute, so we don't actually need that column though. Alright, so now let's work on plotting this and see, what our simulation looks like. So we're going to want a range of times to plot. So we can do np win space. We're going to go from 0 to t end, and we want maybe 500 points. Right, and then we're going to want to calculate the concentration of A and the temperature for each of these times. So we're going to use, so we're going to have the concentration of A and the temperature are equal to sol, so that's the attribute that we had up here for all of the t plot times. Alright, so you can see then CA is an array, should be 500 points in there, and then temperature, that's also an array, and you can see these look like temperatures, so should be good. So then next let's plot. So here we probably don't need this anymore, and you wouldn't be able to see the plot, so we'll make that small. And so alright, so fig is equal to make subplots, and then so we're going to want to make two different subplots because the temperatures are going to be in the 300 range, so the times will be the same for each. The temperatures are going to be in the 300 range, but the concentration of A starts at 0.5, so those are not going to be anywhere near each other on the graph, so it's probably best if we split the graph into two instead of like superimposing them on top of each other. So to do that, we're going to want one row of plots and then two columns of plots. So then we just have like two plots right next to each other. Alright. So then we can go fig.add scatter, and then we'll have our exit values are our t plot values, our y value. So this first one we'll just do concentration of A, and then we'll have our mode is equal to lines, and then we're going to want to put this one in row 1, column 1, so this will be the first plot that we see, and then we can name this, and we'll name it concentration of A. Alright, and then and then I'm going to copy this so I don't have to type it all out again, but this time we're going to look at the temperature. Again, we want the mode to be lines, row is 1, but this time we want the column to be 2, and the name will be, temperature in reactor. Alright, so let's see what we get. Alright, so we've got some nice looking plots here. We can see that when you change the temperature of the coolant from 290 Kelvin, or what was it? It's 300 Kelvin to 290 Kelvin. The concentration of A is going to go from about 0.5, it'll get up, or well, it goes from 0.5 because that's our initial value, and it goes up, past 0.9, so like 0.95 range, and then this is in the first 10 minutes, and then the temperature goes from, so this is the temperature inside the reactor, because we know how the coolant temperature changes, but temperature inside the reactor goes from 350 Kelvin down to about 312 Kelvin over the course of 10 minutes. So that's pretty cool. We can see how that works without having to, build a whole reactor and simulate it out in real life, and actually do it in real life. We can simulate it and, see what these changes in temperature would be, and such. So, alright, so let's try our second one, and that we're going to take the temperature to 305 Kelvin. So, so instead of 290, we're going to put that at 305, and then we can enter everything back in, and let's see how we get. Alright, so you can see this one's quite a bit different. It's not as nice, not as smooth. It starts at, concentration of A starts at 0.5, goes down to almost 0, and then, and then kind of just oscillates back and forth between, 0.2, almost 0.3 to, almost 0, and just oscillates back and forth for, longer than the first 10 minutes, but you don't really know how long because I haven't, increased the time at all. We can do that and see how it looks in a minute, but let's look at the temperature first. So, temperature, you can see, starts at 350 like it should. It goes all the way up to 300 or 440, so it's, that's a almost 100 Kelvin temperature difference. So that's one of the importances of simulating things, because that's quite a big temperature difference. You might not want to do that in real life. You'd have to make sure that your system could handle 100-degree temperature change, or 100 Kelvin temperature change. And then, and then it goes all the way back down to 360, and then it goes all the way back up, and then oscillates between 360 and 400. So that's quite, still quite a big temperature change, and that's why you want to simulate things. So maybe we can see, if we do more than let's say we go out really far. No, that's not what I wanted you to do. Alright. And then, so we can see, if we take this out farther, does it flatten out? And it doesn't really appear that it's going to flatten out, anytime soon. So it looks like it just keeps, oscillating back and forth for a while. So, yeah. So that is how we would simulate this kind of problem.